Today, I want to talk about our experience in building a scalable time series database. I know this is mostly a MySQL conference, but hopefully you won't hold it against me that we chose to use Postgres. Although I think these things are much more, more similar than different. Although that might be a religious debate. I'm Mike Friedman. I'm the co-founder and CTO of Timescale. I also actually double as a professor of computer science at Princeton. The problem which we're setting out to build is that what we start seeing is that time series data is actually happening everywhere in some greater volumes than we've ever seen before. Whether or not that's IoT in terms of industrial machines, we are adding sensors to containers and actually using this as part of shipping and logistics where we can real-time track where all of our containers are moving. Certainly a big thing you hear is in the DevOps community is monitoring and metrics. Even financial trading is a lot of times tick data, both trade data, actually the price of securities data. We have time series data all over the place. Now what's interesting, this is actually from Percona actually put out this survey and asked what database for time series data. And I know there's a number of Percona people in the audience. They divided it in an interesting way, which is showing how relational databases got 32%, Go, MySQL, and Postgres, and all these other NoSQL had a lot fewer. But actually, that's because a lot of times these NoSQL databases are broken apart and accounting them for each of them separately. And so you add together the NoSQL databases, what you found is that over 2/3 of the people, respondents, about 1,100 some respondents, said that for time series data, they were actually using NoSQL databases. And so one question which we should ask is why so much NoSQL databases? And in fact, I think one of the panel discussions this morning asked, do you think you need a special database for time series data? And actually, my co-founder, Jay, I think tomorrow will be giving a talk about what is time series data, why might we need a time series database. I perhaps want to more focus on what we've done at Timescale. But if you press people a little deeper and say, why do you use NoSQL databases, you generally hear one of two answers. Either it's because we don't like writing schemas, or that Mongo is web scale. I don't know if people remember the videos from about 10 years ago. Relational databases have trouble scaling. And this is a partially funny argument, because if you actually break these down, schemas give you efficiency. And in fact, Postgres and MySQL and other relational databases aren't static beings. They evolve with the times. And if you actually look, both of these databases now have very nice support for just taking in JSON blobs. And in fact, they could even do sometimes more advanced things. You could actually get better performance out of a relational database using JSON, schemaless JSON, than you can out of a NoSQL database using schemaless JSON. You could get things like constraint validation. The query planner could do it a little bit with it. You could do a little indexing. But they certainly have some rich ability to handle these types of schemas or schemaless data sets. So then the really question is it actually due to scalability? And for that, I want to kind of break it apart. What was the historical reasons why we thought relational databases had trouble scaling? And there are really two issues that we saw in terms of performance. One was in terms of scaling up. There's really two components. How well do you run on one server, and how well do you run across many servers horizontally? And for scaling up, traditionally the problem, or one of the bottlenecks, is that if we start needing to swap from disk to do all of the type of inserts or queries that we want, that is really, it turns out to be our performance bottlenecks. So how can we design these systems differently? Let's say that we can make better scaling up because swapping from disk is so expensive. Whether or not your hard drive or SSD, it's still really expensive. In terms of scaling out, traditionally, the reason NoSQL database or relational databases had trouble scaling out is that transactions across machines are actually quite expensive. So some of you might have heard of, Google just launched Cloud Spanner. This was a really neat technology that they had built previously. So what Spanner does is, in the end, it's doing two-phase locking across multiple machines. And if you remember, and each of those locks that it takes is actually a replicated state machine protocol in a Paxos group that does 2 rounds of two-phase commits. So if you actually think of one transaction that is lock, modify, unlock with 3 nodes, you're actually talking about around 18 two-phase commit protocols running in order to do that one transaction. That is why fundamentally these things can become more expensive. So what about NoSQL? Well, 2 things. One is if we talk about time series, maybe this just isn't a problem. Because actually, most times with time series, you're not dealing with transactional updates of data. And in fact, NoSQL doesn't solve this problem anyway. So the reason you could say maybe NoSQL had a better time scaling is because they actually weren't trying to solve the same problem, which, by the way, you probably wanted for traditional business data, but actually you maybe don't need for time series data. So if we don't need this, can we bring back that insight to the relational database and then make it much easier and much more performant to scale? So this is all kind of abstract. Let me give you a concrete trace that we ran from Postgres. And I imagine that you see the same results, or roughly the same behavior running this on MySQL. So here is one node running the latest version of Postgres on a pretty well-provisioned Azure instance with premium SSD storage. You're inserting time series data one row at a time to this database. Doing one row at a time, you start around 15 or 16,000 inputs per second. Each row is about 10, if you're a metrics person, 10 metrics. So this is 150,000 metrics per second. And your database grows. You insert data. Time series data keeps coming. Looks good. And then we run into a big problem. Right? So what happened was, well, we're indexing some of these rows. Our indexes, our B trees are no longer fitting all in memory. And so we're swapping to disk. And this basically keeps going on. And what you see is, certainly the average drops, but perhaps even worse, the variance grows really big. Right? The variance has grown so that a lot of these transactions, we're seeing performance in the order of hundreds of transactions per second, or hundreds of inserts per second. Why it's happening? Well, as the table grows large, as I said, the data indexes are no longer fitting in memory. And the key thing is that while you might be inserting time series data, the time is kind of always going forward. You also want to do these secondary indices on other columns that you have. Right? And those secondary indices are now trying to insert to a random location in this ordered B tree. And so that's going to need to swap random places from disk when you're larger than memory. And in fact, it grows worse the more indexes you have, because now you're actually maintaining a separate B tree for each secondary indices. And this problem is only compounded. And in fact, I/O amplification makes it worse. So you could say, so one of the reasons this is bad is because on a relational database, you will be writing data often at your database page size. In Postgres, it's about 8K. I don't remember the latest in MySQL, but probably roughly similar. Page size in MySQL. Depends on the engine, but 16K, 8K, roughly the similar stuff, because you're not writing individual cells. So that means if I want to update a random cell in my B tree, I actually have to swap in the whole B tree page, evict something else, and we actually have that. Writing one cell could be dealing with memory access at the order of 8 to 16K. Right? And in fact, it doesn't really help to shrink the database page. You could say, well, our database page is too large. Of course, every time you try to access a random place in a hard drive, you're doing a seek, 5 to 10 milliseconds. You could say, well, Flash got rid of that random no seeks in Flash. It doesn't help, because Flash actually still reads and writes at the page granularity on the Flash DIMM, which is, again, 8K, roughly. So if you want to actually read one cell, one byte from a Flash, you need to swap in 8K off the actual Flash cell into the buffer cache. Modify, read in 8K, write in buffer cache in the Flash, write out 8K again. So you're kind of limited, and that's the I/O amplification we see in these type of systems. So enter, NoSQL. Maybe actually NoSQL solved this in a little different way. And about a decade ago, we started seeing the emergence of kind of new types of data structures. So a lot of these systems actually started adopting, perhaps one of the first that really popularized this was Google Bigtable and then LevelDB. And we now see this in actually Cassandra, the new WiredTiger backend for Mongo, in Influx. They all have these things called log-structured merge trees. And what log-structured merge trees observed, let's actually avoid that type of I/O amplification. So let's avoid doing lots of small in-place updates on disk, which is what we need to do to update that B tree that we talked about before. And so what they did was basically they kept all of the recent modifications, all the inserts, actually updates, all the deletes. When you delete something, you actually don't delete it from disk. You just leave a little tombstone that says, I deleted this. Just leave a marker for that. And you basically buffer them up in memory. And then once you hit a certain enough batch size, you commit that as one atomic, immutable, sorted batch to disk. Right? And so then you can kind of align that. If the minimum things you could write your disk is 8K, well, let's wait till we have a whole bunch of operations where you could write in 8K as a time. Right? Now, the problem is you don't have any global sorted order of your your whole data. It's not like you have a B tree where you could traverse the entire thing in sorted order. If you want to do a lookup, you kind of have to go through these stages. You first check your memory table, then you check one or more of indexes that are pointing to each of these individual batches. Now, in the background, it's called a merge tree because you might take these, you merge them together, you resplit them, do all this asynchronous work. But in general, you're actually touching a whole bunch of different of these indexes to look it up. And for performance, you end up often keeping a lot of these indexes in memory. And so effectively, what this translates to is we've avoided disk I/O at the cost of actually needing a lot more memory. And I think after today, I think Paul from Influx is going to be about some of their work that they've been doing to deal with high cardinality data in a lot of these systems. And I think at least the previous or the current version of Influx, the size of your memory grows with the cross product of the cardinality of each of the columns you have. Which means, for example, if you want to index 1,000 different devices at 100 locations with 10 firmware versions, you need to, just for that, you need to keep about 10 billion entries in memory to index that. And so really what happens is we have large memory use, and a lot of times you have poor secondary index support. You can't, for example, index numerics because their cardinality will just kill you. Those turn into full table scans. OK. So what we want to do when we're setting out to do time scale is ask, is there a better way to solve this scale up problem for time series data? And in fact, we're not saying, you might ask, well, isn't scaling, a SQL database like this grand challenge for 30 years? What did you guys know that all these smart people didn't know before? And the answer is we're trying to solve a different problem. And we're trying to solve a different problem because time series workloads are different. And if we're trying to build a database for time series workloads, then we could define it architecturally for that workload, as opposed to a general OLAP or general OLTP database. In this example, if you compare time series workloads compared to OLTP workloads, for example, the canonical banking system. You have a bunch of users. You walk into Bank of America, withdraw money, transfer a different account. It's a transactional update to 2 rows, right? So primary updates between 2 random account IDs, and writes will be randomly distributed over this table, as opposed and transactions often to multiple one of these. And here it turns into the problem when you want to scale. How do we then do distributed transactions? Time series, primary inserts, not updates. Writes to the recent time interval, not to the randomly distributed. And writes associated with a timestamp and some primary key. This was a data point in IoT. This was a data point from this device at this time. In financial, this is a tick about this financial security at this time. It's timestamp and primary key, not transactions to multiple primary keys. And so this workload difference is really what we leveraged, which thinking about the data model and scalability inside timescale. So again, let's look back at our, just visually view that. If we think about, let's say, the IoT setting, we have data streaming in from everywhere. Data comes in. The newest data, and this is supposed to represent data coming from different sensors across different time intervals. Now, before we talk about what we actually do, let's actually think of some straw men. So you might say, well, and I kind of was already alluding to this. You might say, well, can't we just use time as the primary index? And doesn't that solve all of our problems? Because, as we just see, you're largely writing to the latest thing of time. And wouldn't that just stay in memory, and all the old stuff will be disk, and you're done? And that, it's true that writes are to the recent time intervals. But I kind of already suggested that if you want to index anything else, they're still over your entire table, and you're back at square one, and you're doing random, inserts to random parts of your table. And so what we actually do instead is a type of adaptive time, what we call time-space partitioning. Time, kind of visualized here as the y-axis, with space as some type of primary key, like devices or security instruments or assets or servers or locations. And interestingly, we actually use this type of partitioning for both, really this common mechanism for both scaling up and scaling out. So everybody uses sharding for scaling out. It's actually a lot less common where you see it play such a central role in actually scaling up performance, even on a single server. And so not only is it playing this new role, but we actually have this common mechanism when we take us from single node to clustering. It's actually the common mechanism on the insert path and on the query optimization that we're using basically both for single node and for a clustered environment. So let's actually ask, so that seems normal. And you say, and you might think, well, everybody knows how to partition now. Here you might hash partition on the primary key, and maybe here you partition by a fixed time interval, let's say every day. You even see some people trying this themselves. I remember I was talking to a person that says, well, we were using DynamoDB on Amazon, and the volume, DynamoDB is one server. The volume, we have way more data. So they actually set up a different DynamoDB server per day. And one day's data would go to one, and one day's data go to another one. And they would, at the query part, people writing their SQL queries would need to then select from many different databases, and joining application spaces was a big mess. But what they were doing was the really first thing people always think about is let's just use static fixed durations for partitioning. And you could often express this too in various partitioning features in Oracle or in other databases. The problem which we have is that your data volumes can change over time. So if your data volumes are static, you might see this nice behavior where each day you have the kind of the right size data. And I'm going to use kind of the right size to mean a good size, so it basically fits in main memory. Unfortunately, you have deployed 1,000 devices, and now you just shipped your next 10,000 devices. Or you all of a sudden see this huge spike in your new app because you want it to grow. You elastically grew the number of servers you have, or you grew the number of front-end servers you have on Amazon, and now you're actually sending a lot more metrics to your system. And so what happens is with static data, you actually have to deal with this increasing rate forces these chunks to be too large. Conversely, you say, well, actually, what I really want to do is have a target size. The problem here is I was using the wrong criteria. I was doing it by time. What I really want to do is do it by size. It seems natural. The problem, again, is kind of the same thing. You don't know exactly that the order of data is always going to come out, that the wall clock time arrives at exactly the same time. Sometimes data will come early. Sometimes it'll come late. It could come early even because your clocks can be unsynchronized, which happens in the production world. And so if you actually define the intervals, because you might want these intervals to be disjoint, based on the time that arises, and you're only going to kind of close a chunk after you hit a certain size, early data can greatly expand out the size of your chunk and, again, leave you in a bad spot. So what we actually do is use the concept of adaptive intervals. And what this means is that we actually create these partitions with fixed time intervals, but actually the interval could adapt to changes in data volume. So if you're have increasingly data rates, your windows can get smaller. Similarly, if early data will be pushed out to a future chunk as opposed to grow the current chunk to be much too large. And that is kind of how we find the balance between trying to deal with well-designed time intervals and target sizes for these actual chunks. What this actually leads you to, and I kind of was alluding to this already, is that partitions now become right-sized. And that is that recent partitions, which are generally hot, which are in use both at write time, and if you're doing something like dashboarding, that's often where a lot of your queries are going. You might have historical queries which span a long periods of time, but a lot of your real-time dashboards are all touching your recent intervals. These are already all in memory, which means both insert path, which you saw, and query path becomes more efficient. It also, this type of time alignment also, and this type of partitioning even on single node, gives other benefits, such as for automatic and efficient retention policies. So if you decide that, I want to keep a lot of this data, this is a pretty common thing, particularly for metrics and monitoring, but I, let's say, only want to keep raw data for a month. Right? With one table, you could do that. You could write a manual delete message. But what that is actually doing is deleting from inside a table is actually just removing those rows, which are effectively deleting an internal part of the file, which is basically fragmenting your file, which means that in your database, you'd have to run vacuuming to basically defragment your file. And it turns out this really does not work well for very large tables when you're competing against also insert path. And sometimes you can't even do this type of vacuuming. It's a really bottleneck, particularly in Postgres. With our approach, actually a policy like delete data after 30 days is literally just dropping a table, which translates just to deleting a file on disk. So it's really efficient. And it turns out that as I was showing this partitioning, this was the notion of that square abstraction split into individual partitions, individual tables. Like I said, these partitions can actually reside on one server, or actually the way that we do it in timescale is this is how we're actually distributing data over many servers. These partitions are spread around servers. We don't actually use any type of centralized transaction manager or specialized front end. All the nodes are homogeneous in the extent that they could all actually take in insert queries or inserts or select or queries for any data. And if you're inserting a single row, one node could route that row insert either to a local table or a remote partition, or you could actually insert large batches or copy large batches onto one node. And that node will efficiently create sub-batches out of that one insert batch and route those sub-batches to the proper partition to be inserted while minimizing the amount of locking you need to do. So we've actually spent a lot of time thinking about how to make the insert path very quick. For those who are less familiar with Postgres, you actually have a lot of power in building on top of Postgres as an extension. About half our code is written in C, the fast path. And the other half is written in Postgres scripting language, PL, PG SQL, that allows us to do a lot of the management. The interesting is this partitioning is not only how we deal with inserts, it's actually how we do a lot of our efficient query optimizations as well. So for example, one thing we do is we tie into the query planner, and we actually take the query plan, the parse tree, and rewrite the parse tree knowing what we do with partitions. And we could use information we have around these partitions to do things like constraint exclusion. So if you are querying, you query what looks like one giant table. All our data looks like one giant table to you, but if you have a rich predicate that slices out some time or slices out a device, so for in this example, select time temperature from data. It just looks like one big table where something in the last 7 days and a particular device ID. And so the query planner will know that this device ID corresponds to this set of partitions, and also these are the ones corresponding to the last 7 days. And so it will constrain the parallel query to them, and then it would then execute this query in parallel across these 3 partitions, but nothing else. And on those 3 partitions, it could use the local indexes defined on those partitions to make those queries fast as well. Similarly, you could slice horizontally. Now, if you want to look across all your devices in the last 24 hours, you might actually select a different set of partitions. And we even actually added support, because we have this notion of time, we could build special query optimizations around time. So one thing that we, for example, added was this type of merge append, which is almost like an insertion sort of time intervals across partitions. So for example, time bucket, this is a particular function that we actually define UDFs better support than just the truncation they allow. So give me the average temperature per every 15 minutes for one version of the firmware where my Wi-Fi quality is less than 25%. So this could be, you had a support call that said all of a sudden some of my devices seem to be overheating. And you might think that my device is overheating because it actually doesn't have a strong Wi-Fi signal and it's keeping swapping on and off. It's power cycling, let's say, it's radio. And so you want to evaluate this. So this is the query you might run. Group by every 15 minutes, order by 15 minutes, and give me the last hour and a half. Give me the last 90 minutes. Right? And so what this query actually could do, one of these optimizations, is rather than also, because this might be a more complex query that actually has to scan through a bunch of data, our optimization, for example, will find one value on this, because again, this is limit 6, and then is going to incrementally take back, based on this order by, the maximum until it hits 6, and then it's going to be able to stop the query. Okay? So there's a bunch of optimizations you could even do by incrementally processing data in parallel on multiple of these partitions. And I'll show you later a little bit about the performance benefits we get from this optimization compared to, again, like a vanilla planner and a vanilla Postgres. Other optimizations we do, partial aggregation pushdowns, keep metadata to be able to ask questions about the last k records. So you might want to say, give me the last give me the last 3 readings from each of my devices or each of my servers. And you have efficient optimizations for that as well. So all this is together is what we ended up building, Timescale, is that we want to make basically full SQL scale and be easier to use for time series data. And I already was alluding to this a little bit, that we are packaged at a Postgres extension, which basically means that we could, it's not a fork, it's an extension. You could take an existing Postgres server and just install us as a plugin, basically, to that operational server. And so what that gives us really is that we are designed for this full SQL, fast index, complex queries, and reliable in that, in terms of ease of use, we support full SQL. And really, we could connect with any client or tool that speaks Postgres. You don't need to write special connectors. You run Tableau, it looks like a Postgres database. Power BI, Postgres. Stick up PG admin tools, it just looks like Postgres, right? And if you want to peel back the covers a little bit, if you're a DBA, you could actually see, and if you run explain, MySQL, does MySQL have this equivalent? You run explain, you can actually see the query plan. That all works with us. You then will see all these subtables that we've created under the covers, not necessarily the code paths, but you can see actually the query plans that it's doing on top of these tables. So easy to use, scalable, high write rates. I'll show you some benchmarks, time-oriented features and optimizations, complex queries, complex where predicates, group bys, and whatnot, and reliable. I think the interesting thing about this is that we have not, since starting this, we have not actually been worried about losing data. You typically are with experimental databases. If there is a bug, it's not that we have lost data. It turns out that as we're developing new features, maybe we didn't. The right path was in our development branch, of course, never the production branch. The development branch maybe had a bug that didn't insert data right, but we're not worried about losing data because we basically stand on the shoulder of giants. What Postgres and similar with MySQL have done over the last 20 years. And so I kind of wanted to just touch on some of the high-level features again, which I was already alluding to, in that from the user's perspective, this really just looks like a SQL interface. It gives you the illusion of a single table, and you select against a single table, and underneath the covers, it's hiding this complexity of this distributed query optimizations across partitions, even when running on a single node. Insert, you could again insert into a single table, an individual row, a whole batch, and it will figure out under the covers how to do all the proper partitioning on a single node or in the cluster. And it will also, you don't actually really configure partitions at all right. I'll show you the one-line code it takes to set that up. But you don't actually manually close this. You don't manually set up triggers. This actually happens all automatically. And it automatically creates and closes these partitions, both on the time interval and the table size, to do that type of calculation I was describing before. One other interesting thing is because it is just SQL, it actually allows you to support things like joins, which you really do not have in most NoSQL databases. And so if you look at most traditional time series databases today, they generally do one of two things. They either denormalize their data, which means that with every row, they might actually store that additional metadata. And so that is, of course, inefficient because you're storing that additional metadata. It's expensive to update. Because if you want to update, you actually need to rewrite all of your history, which could be prohibitively expensive. And it's actually operationally difficult, because it really means that some type of application is joining this thing before it ever even gets written into your database. Alternatively, perhaps the more common thing is that you actually often will deploy a separate relational database to store your business data or your metadata aside of your time series database. And then what will happen is you'll actually join them in application space, which is certainly a pain. And it's kind of funny. The whole reason we have database management systems is to avoid requiring the developer to manage a lot of this type of stuff, right? And now we're basically back in this era where we're creating these data silos that it becomes hard to combine. What I actually didn't start, I didn't really start with a backstory about one of the reasons we built Timescale is when we started out, we were actually building more of a data analysis platform for IoT devices, which is probably why you saw a lot of examples being IoT. And we ended up trying to evaluate a bunch of the open source tools or the NoSQL databases especially, and really weren't happy with how they gave us this choice between the power of SQL and the reliability and the scale of NoSQL. And we initially had tried a NoSQL database before we ended up building this to solve our own problems. And we commonly would have this problem that this customer would call and say, oh, I'm having this problem with this device. And we'd say, like, oh, I know the customer's name, but I forget his user account ID. And then if he tells me a particular device, he told me his device name, and I didn't remember exactly how that mapped to my device ID that I was using in the database. And so we would manually be looking up in a relational database for this information, and then using that to query our time series database. And this was a huge pain, especially for even things like customer service and debugging, right? Because you have these big data silos. And that was really something that you could avoid, again, if you could just do joins in the database. And so that is what you could do if you have a relational database. You could store relational tables inside Timescale itself, or you could actually store in another external database. And Postgres, for example, and I'm sure MySQL, gives you the rich ability to, for example, even import that as a foreign table into yourself and then query it via a foreign data wrapper. And so you could do joins directly inside the database. And internally, we support this either if data is very large or fast changing by having that data stored on one node, or if it's either smaller or slowly changing, we'll materialize that data across the entire cluster, and then could do local joins for more efficiency. Again, because we're built on top of Postgres, and we are kind of cleverly reusing our partitions as mapped down to actually underlying Postgres tables, this actually gives you familiar management that I already kind of alluded to, that you can connect to it and query it like it's just Postgres, but also in terms of management, you could run all your existing tools and manage it just like it's a Postgres instance. You could use the existing forms of streaming replication inside Postgres. You could use the existing checkpointing and backup or fine-grained access control. And all of those basically operate like they would in standard Postgres. Similarly, if you want to change you want to alter the database, alter the schema, you could just, again, alter the hypertable, the parent table, and the system will translate that down to altering all the subpartitionings. So in many cases, you don't need to manage the subpartitionings if you don't want to. That kind of happens automatically. And again, because it just spoke Postgres, it basically we don't need to write special connectors. You can just point any tool that speaks ODBC or JDBC or Postgres towards the database. And from their perspective, it just looks like Postgres. I kind of alluded to this already. And in designing this, we thought carefully about how to kind of reuse and improve on the existing Postgres mechanisms. So this is getting into a little Postgres weeds, so maybe I'll do this quickly. But actually, these partitions are just stored as child tables in Postgres of a parent table, which is our hypertable. And I already kind of suggested that these secondary indices are local to each partition. But on top of this, Postgres gives you some support. So if you in Postgres would be to query the parent table, it would actually send the same query to all the child tables. And it would do the parallelization, but often you would be touching all of them in parallel. And so in Timescale, what we've done is we provide a lot better constrained execution to avoiding touching all those querying children. I already talked about some of basically the new time and partition-oriented query optimizations we did, and some of these time-oriented features which we've added. Similarly, in terms of inserts, even though we're using the high-level kind of parent-child structure, we kind of, again, insert in this fast insert path to really give more efficient inserts, avoid a lot of locking, kind of do things by avoiding a lot of expensive upcalls into scripting language and sorting features that you normally would do, caching tables, all these optimizations we do, auto creation and closing the partitions. And this is all to kind of make this quite performant. And the last thing I kind of wanted to suggest about familiar management is just, for example, why creating or migrating these things are pretty easy in Timescale, or so easy in Timescale. So for example, creating this table I described, I've been talking about so far, time, device ID, temperature, humidity, is just like any old create command that you would do in SQL you learned in class in 101. All the magic is happening here. Create hypertable. Give us the name of the table you created. Tell us which is which one of the columns corresponds to time. Could support timestamp Z, big ints, whatever. Which is your partition key, and everything else is taken from there. And in fact, migration, that will work. So select an old data that's not a hypertable, insert it into our new hypertable, and it'll do all the partitioning for you. So with that, I want to kind of leave with some, I spent a lot of time talking about architecture. What does this actually give you? And before I show you graphs, let me just remind ourselves conceptually what this should give you. One, I talked about we did carefully sizing chunks to keep things in memory. Some of this partitioning allows us to reduce the amount of data read. These merge append operations or some localized group bys could optimize the amount of data we need to read. Two, even on single nodes, if you have multiple disks, we can now execute queries both in parallel across multiple chunks with using multiple threads to parallelize queries, and also with multiple disks to parallelize I/O off of multiple disks. And in a clustered environment, we could reduce latency by, of course, parallelizing these queries across many servers, and by doing some things like pushdowns, aggregation pushdowns, this merge append could be pushed down. We could, of course, reduce the amount of network traffic because we don't need to join this data across the network. So let me show you some graphs. This so far is single node. And I should say that at the end, I'll say we open source released it. The current release, the beta release of the open source is just for the single node. The cluster has been run. The clustered version, is where we came from with an IoT platform. Has been running in our hosted version since last year, since last summer. But it'll probably be a number of months till we repackage it and work it out for an open source release. But I started you with the same graph we saw before. This is again Azure Server. Single row by row sort of Postgres, and now we're left with timescale. So pretty remarkable performance difference. And the most kind of remarkable thing is really the constant time performance across, basically this is up to 250 million rows of data across the system, while Postgres gets this high variance. We think of these terms as rows. This is 14,000 inserts per second. When you talk to a lot of metrics people, they think of metrics, which in our mind is a column. So this is around 150, close to 150,000 metrics per second per server. Now you could say, well, 4 gigabytes of memory, that's not really fair. Let's make this bigger. Let's make it 16 gigabytes of memory. Again, this pushes out the problem for Postgres. But eventually you run out of main memory, and you start going to disk. I think it's interesting. Time series data is one where it will ultimately expand to grow whatever storage capacity you have. And if you could use a fully in-memory database, that's good. But sometimes you actually need to swap to disk. And this just pushes out the problem a little bit. So Postgres starts out better, but again, exhibits its performance. Timescale stays constant. And I said before, you could insert data as a row by row, 10 metrics at a time. Or you could insert data by larger batches. This batch size was actually chosen. We kind of built our benchmarking around Influx's actually benchmark tools. So we kind of wanted to just use whatever, not necessarily construct ones that we think are optimal for us, but use kind of what another NoSQL database was doing. And so they actually insert things in batches of 10,000 kind of rows at a time. So we ran that us and us. And Postgres, off the cliff. And timescale, you get a little bit of variance. But we're still at around now 1.3 million metrics per second. And I should say, I think this week we hit a new PR got pushed that improved that by about 8 to 10%. So you constantly push up the hill a little bit further. And notably, this is about on a single node, same hardware, same everything. This is a 15-time performance improvement over Postgres, even though we're building on top of Postgres. We're just using it in a particular way designed for time series data. Now, if you look at the query side, there are certainly some queries which you see similar performance with Postgres. And I think there's still a lot of specific query optimizations we're going to do. Sometimes you're getting some 20 or 30% improvements, performance improvements, just because of some of the ways you localize the data. And you don't have to walk as big your B trees. But for example, I spent some time talking about that merge append optimization before, if you remember. And that was seeing a 22,000%, 22x performance improvement over Postgres because of some of the optimizations you could do. So I think there's a lot of work to be done there. This is actually this particular query I'm doing for here. But there's a lot of, again, once time becomes a first-class citizen in your query optimizer, there's a lot of things you could do. So I think I got a slide. I have about 8 minutes left. And I want to leave with, timescale is not designed for every use case. I think it's important that we be frank and honest about what we're good for and when we're not good for. So I should say, there's a lot of nice NoSQL databases out there. And if all you need is a simple key value lookup, or if all you want to do is a single column rollup. That is, you just want to know, the CPU metric over a month and just do a quick rollup there. We're not designed for that. Probably some type of column store is going to give you better performance for that. Right? Similarly, again with the column stores, if you really desire that, you really need heavy, heavy compression. We're again not currently at least. There's some things that we're working on with both compression and some of our data model, but that's not been our priority compared to things like column stores. And if you're dealing with very sparse or really unstructured data, Postgres, for example, does store nulls efficiently. They're just like some of them are free. They're just little bitmaps. So there is some benefit. But if you have a wide row of 100 possible columns and usually 90 of them are sparse, again, something like column store will probably be better there. However, if you want full SQL, you want complex predicates, you want aggregations, you want joins, you don't want to worry about, is this SQL-like language work? And the other thing about SQL-like language is there's two issues of it. Sometimes as a user, you often don't know if the query language could handle the query you want. Some languages, for example, allow you to group by time, but you can't group by anything other than time. We quickly found that when we're running trying to do this for our own sake. The other big issue is you often can't connect this transparently to tools. So not just that user, but I want to be able to throw my customer service runs this Microsoft reporting tool that speaks SQL. I want to be able to throw that at my database. In a SQL-like language, you couldn't do that. You could, but that happens automatically if you're just running something like Postgres or MySQL. You should use, again, if you want rich indexing, mostly structured data, or you basically want the whole ecosystem of a database like Postgres. So with that, as I said, we had an open source release. Was actually just last month. You can go here. It's released under the Apache 2 license. The beta release currently was just for the single node, though we're working on the clustered version. The interesting thing here compared to most clustered databases is our mechanism, both insert and query, for single node and clustered are actually very similar. Visit us at booth, I don't know, near where you go in for lunch. And subliminal message of stars. Please give us a star if you liked it or liked my talk. Otherwise, a lot of the stuff from this talk, just last week I posted a fairly long, somewhat technical blog post on our blog. Feel free to read it and send us any questions you have. Otherwise, any questions?
What's your business model, and do you foresee continuing to contribute to your development of open source?
So the question was, what is our business model? It's interesting also given that Paul from Influx talked this morning about open source business model. I think we're perhaps maybe a little less pessimistic than he is, in the sense that I think by now, partly two answers. One is, I think if you ultimately want to build a database that actually becomes widely used, you effectively have to be open source, because you only want to be trusted unless you're talking about very niche use cases, very specialized use cases. You want to be only trusted in operational scenarios where people know and have a trust that your software will persist and the company won't just go away. And this is why I actually think that we were just at this Postgres meetup that FINRA, one of the largest financial commodity information fields, just moved from Oracle to Postgres. I mean, this is happening all across the industry. The second answer is I actually think that there's, we plan, like I said, we open source a single node. We plan to make the clustered version open source. But I think there's also certainly still a number of features that are really important much more for enterprise. And so we'll also have an enterprise license for those, as well as the common thing for probably a hosted version or whatever. But I think there's now a model between enough companies who've done the open source path that are doing well with that, Mongo and Elastic and other companies, that I'm not as worried about this, and we're just focusing on getting timescale out there and getting use.
I'm wondering, what kind of testing you guys are doing as far as where you're generating data, and are you going network, or locally generated data like this?
So the question is, what type of testing are we doing? Somewhat a variety of stuff. A lot of the benchmarks here you're seeing was actually server up, and we're actually pushing data to it. We have been running. It's not the exact same code base as the open source release, but we have been running effectively a version of this database in production for our customers on our hosted version since approximately last summer. Something like close to 100,000 IoT devices from all over the internet, maybe some of them in your homes, are streaming data to our platform. So that's a test. And part of the open source, we're actually just this release setting up our database on the side of our production things to kind of use that traffic as traffic generators to continually knock on our database. We're deploying it for our own, the metrics from our hosted servers. We're deploying this as the backend for our metrics. And so we're kind of doing all of the above in that we have traditional unit testing, we have traditional workload generations, and we have basically production workloads.
Can you list some main reasons why you choose Postgres, not
The question is, why Postgres and MySQL? I think I almost want to take the fifth on that, given this audience. But why don't I actually punt that to Matt there, who is, I think, didn't you raise your question to answer that? Who's one of our core engineers and was kind of central to this discussion, or to this decision.
I think the answer is simple. We didn't want to fork anything, and it's a lot easier. So MySQL gives a very good hook into the storage engine, but it's very hard without forking to do work inside the file.
so it has to depend on the native function?
Yeah.
And Postgres is the opposite. Postgres doesn't really have a pluggable backend, but the extension modules allow you pretty deep path into like the query planner and the execution engine, which is really what we leveraged heavily. Ideally, a database would have both. You could both hook into the query planner and hook into the storage engine, maybe for a future time. But I imagine, I should say, I imagine the architectural decisions we made here, I think probably would also fit naturally within MySQL. Because this was more about the architectural ways we design this as opposed to the details of, in a relational database, as opposed to the details of Postgres or MySQL.
Just kind of referencing your performance comparison slide, have you done that with any NoSQL databases?
We have internally. We have not yet released these numbers against several of the NoSQL databases. I would say at a high level, the reason sometimes I should say, benchmarking is an art, and it's lies, damn lies, and statistics. In that, what we're trying to do is we want to be very fair about the type of benchmarking we do, because I think the last thing everybody wants is us to release one measure and say we are 30x better than whatever on this, and it's for one particular query on one particular thing. And if you even look at most of the traditional TPCC benchmarks and whatever, those benchmarks themselves are very opinionated. So I don't think there's any great benchmarks yet for time series. Even the OLAP-style benchmarks really don't fit the type of time series workloads we want. So high speaking, I think the results were somewhat kind of along these lines, that our compression is not as good as some column-oriented databases. And again, with single column rollups, they will be better. But particularly if you're doing type of multi-column selects or predicates, in some of those we far exceed the performance of some of the best time series databases.
Just want to add to that. The reason we haven't released the benchmark isn't because we don't like them. We actually like them a lot. But we actually want to make sure before you release something that you actually kind of look behind every corner. You're kind of being fair to the other databases, because we hate when people cherry pick benchmarks, and we don't want to do the same thing. So we want to be somewhat thorough with our process before we release the benchmarks. And plus, we release them the way where we can reproduce them. We expect to do that soon, but we haven't.
Yeah, our biggest concern. Yeah, I think so far we've been overly pleased with our benchmarks, which we want to then be very careful about releasing them because we want to be in the game of cherry picking it. It also means the other common question is, well, how do you compare against something like Redshift? And the answer there too is actually quite hard to answer in terms of benchmarking, because a lot of times what things like Redshift or Greenplum or Vertica, traditional OLAP, because they don't focus on time series, they give you tools, but they push a lot of the complexity on to the actual DBA. To set up all your table, to do the adaptive stuff right, to do the query planning right. And so in benchmarking it, there the challenge is, well, do we do a naive thing? And how much do we end up re-implementing all of our optimization and complexity in order to make Greenplum behave well, then we could benchmark again? And that's actually really a hard thing to straddle the line. And that's something that we just haven't been sure on how we want to benchmark against those things yet.
Which DBA to choose.
Exactly. And also, this is all a cost-money trade-off. Like, you could hire, well, you can't hire our team, but maybe you guys could pay them enough so that after a year of hacking, hardcore hacking by very, very high-quality thing, you could recreate it. That's true about anything. And then it's just a question of cost versus time. Any last questions? Great. If you want to find more, like I said, blog posts, we also have a fairly detailed, like I said, I'm an academic, so I can't help writing papers typeset in LaTeX. So if that's your thing, you can go to our website and find that. Otherwise, we'll be around in the booth to answer any more questions. Thanks a lot.